Welcome to The Explainer. Today, we're breaking down the fascinating, slightly mind-bending mechanics of artificial intelligence. We hear the term AI agent thrown around all the time, right? But how exactly do these digital entities actually process this chaotic world to make smart decisions? Essentially, how do they think? Well, we're going to demystify the internal architecture of these agents, mapping out how they go from simple, basic reactions all the way up to complex, layered intelligence. Okay, let's dive into this. Here's a quick roadmap of where we're headed today. We'll start with the AI agent system, move into inside the controller, check out a smart home example, talk about building a belief state, and finally scale it all up with hierarchical control. All right, part one, the AI agent system. Before we even touch artificial brains, we really need to understand the absolute foundational building blocks here. In its simplest terms, an agent system is made up of just two things: the agent itself and the environment it lives in. There's this continuous, unbroken feedback loop happening. The agent constantly receives stimuli from the outside world, and in return, it carries out actions that physically affect that exact same environment. And this brilliantly illustrates that dynamic. Down at the bottom, you've got the environment, pushing stimuli straight up into the agent's body. Now, the body uses sensors to capture that data and actuators to physically carry out actions. But here's the catch. The body doesn't do the deep thinking. It just passes those percepts up to the controller and waits for commands to come back down. It's kind of like touching a hot stove, right? Your skin senses the heat, but it's your nervous system and your brain that process it and shout, hey, pull away. Moving on to section 2, inside the controller. This shifts our focus directly into the brains of the operation. To really get this architecture, we have to firmly separate the body from the controller. The body is strictly physical and reactive. It uses sensors to feel, actuators to move. But the controller, that is the strategist. It takes that parsed sensory data, which we call percepts, and uses its limited computational power and memory to formulate specific commands. But we need a quick reality check here. Controllers absolutely are not omnipotent. Just like us, they're constrained. They're situated in time, they receive sensory data sequentially, not all at once, and because they have limited memory and computational limits, they obviously can't remember the entire history of the universe. So every single command they issue relies entirely on what's called a percept trace. That's just a specific sequence of past and present information they've actually received and chosen to hang on to. Let's ground this with section 3. The smart home example. Abstract theory is great, but let's see what this looks like in practice. Imagine you've got an automated food buying agent living in your kitchen. Its entire universe, its environment, is literally just your pantry and the local grocery store. It has two incredibly simple goals: minimize the price you pay for food and never ever let you run out. The stimuli it's receiving are the fluctuating daily prices and your current stock level at home. Plus, it comes equipped with some prior knowledge about typical price ranges and roughly how fast you eat. Now, what's really interesting about this slide is how the agent's logic plays out over 75 days. We've got 3 stacked charts here: price at the top, stock in the middle, and bot at the bottom. Follow the timeline to right around day 15. The top chart shows this sudden, massive drop in price, hitting roughly $2. At the exact same time, check out the minute chart. Your stock is dangerously low, dipping down near 10 units. Because the agent perceives both a low price and a low stock, boom, the bottom chart shows a massive spike. The agent triggered a command to buy roughly 48 units. It successfully navigated its environment by reading the percepts and executing the perfect command. Which brings us to section 4, building a belief state. But wait a second, how did the agent actually know that $2 was a good price? I mean, it had to remember what the prices were yesterday and the day before that, right? In the real world, an agent rarely gets a perfect omniscient view of its environment. So if it can't see everything at once and it has limited memory, how does it effectively remember the past to make a good decision today? Well, the answer is an internal memory loop. Since our agent can't remember its entire history, it actively constructs what computer scientists call a belief state. Notice that dotted line looping out of the controller and feeding right back into itself? At every single tick of the clock, the controller has to decide not only what physical command to send down to the body, but also what memories it needs to encode and send into the future for its own next cycle. Let's zoom in on the visual pathways inside that controller box. You see a fresh percept coming up from the bottom. At the very same time, an old memory comes in from the left. Inside the controller, these two distinct streams of data actually merge. Then, that merged data splits to do two very different jobs. One path drops down as a command to the body, and the other path swoops back out to the right as a brand new, updated memory for the next time step. Breaking that down mathematically, the controller is essentially running two parallel functions at any given moment. First, you have the belief state function, which calculates the next belief state based on the current state and the brand new percept. And second, there's the command function, which calculates the actual physical action to take based on that exact same state and percept. To tie all that math back to our smart home agent, its belief state is basically just an approximate moving average of grocery prices. The formula uses a 0.95 multiplier for the old average and only adds 0.05 of the new price difference. This creates what's called a discounting rolling average. Now, don't let that term intimidate you. It literally just means the agent is deliberately designed to slowly forget old, outdated prices and weight recent trends more heavily. And that is exactly how it defines its current reality. All right, the final piece of the puzzle, Section 5, scaling up to hierarchical control. So we've totally mastered a single loop. But let's be real. Real-world robots don't just buy grocery chips. They navigate incredibly complex, unpredictable environments. To get there, we absolutely have to scale up. Now, I know this diagram looks a little intimidating. It's basically an alphabet soup of variables over time. You've got belief states interacting with actions, generating observations, earning rewards, altering world states, the whole shebang. If you try to calculate every single one of these variables for every single motor and sensor on a complex robot in one single flat layer, the math becomes overwhelmingly slow. The agent would literally be paralyzed by computation. Let's move to solution and see how this builds into the ultimate solution: stacked layers. Instead of one massive brain trying to micromanage everything, engineers stack multiple controllers on top of each other. And the sheer genius of this is that each controller looks at the layer beneath it and treats it as a simplified virtual body. So the top layer says, hey, go to the kitchen. It doesn't worry about motor torque or wheel friction. It just passes that high-level command down and lets the lower layers handle all the messy physical details. Looking inside just one middle layer of this hierarchy, you can see how wonderfully complex the data flow gets. It is essentially juggling three things at once: high-level percepts coming down from the boss layer above, low-level physical percepts coming up from the layer below, and its own internal memory loop spinning side to side. It synthesizes all of this to pass refined commands down and simplified observations back up. This division of labor is really the secret sauce that makes advanced AI possible. Higher-level controllers operate slowly and strategically. They get a highly abstracted, simplified view of the world, so they can just focus on complex, long-term goals. Meanwhile, the lower-level controllers run incredibly fast. They aren't thinking about the grand master plan, they just react instantly to immediate physical changes, like, say, keeping a walking robot perfectly balanced if it hits an unexpected bump. So the crucial point is perfectly captured in this idea from the source material. A purely reactive agent doesn't have a belief state, neither work very well in complicated domains. Basically, to survive in a messy, complicated world, an AI can't just be a bundle of simple reflexes. It absolutely must build, maintain, and constantly update an internal model, a belief state of both itself and the environment it's moving through. Which leaves us with a thrilling and maybe slightly haunting thought to end on. If the secret to true, scalable artificial intelligence is the capacity to model a belief state of itself and the world around it, what exactly happens when we stack these hierarchies so high and feed them so much data that their internal models become as rich, nuanced, and complex as human intuition? It's a wild frontier, and we are exploring it right now. Thanks for joining me on this explainer, and keep questioning the technology around you.